Okay, that seemed to work. So let's try for round 2. So this is the equation we just derived. And the first thing we're going to do is to find the moment of inertia of a couple of point masses in the following way. So this is the moment of inertia of the apparatus plus whatever stuff is on top of it. Right? So I have this written as I net is I of the apparatus plus I of additional stuff. Moments of inertia are just additive. In case you don't understand how I can just add them together, remember we start with this equation that defines moment of inertia as a sum. That means that if I have kind of a combined system, as long as they have the same axis of rotation, I can just kind of keep adding moments of inertia. So if this is my apparatus plus stuff, and they're all rotating around this axis, if this is the apparatus and the remaining part is stuff, I just add them together because it's summative. So my I net really represents to me the apparatus and whatever stuff I'm putting on top of it. So for part 1, you're going to be trying to find the moment of inertia of the 2 point masses. And we have a comparative equation, remember, mr1 squared plus m2r2 squared. So we'll be using this form to find a value and comparing it to this one. Okay, so what do our point masses look like? Well, they're designed to fit over rods, so they're actually hollowed out cylinders. So if this is my kind of triple tiered rotating object, the stuff that I'm going to put on top of it is a uniform rod of mass m, length L, but also point masses. So these hollowed out rods are designed to kind of fit on top of, hollowed out cylinders, are designed to fit on top of these rods, and then I can kind of bolt them down with bolts. And these spin all around this axis of rotation. Remember, the hanging mass is over here somewhere driving the rotation. So I'll mount these onto the rod. I'll measure their distances away right away. Again, these aren't exactly point masses, so I'll have to go from the center to the center or axis of rotation, from the center of these objects there, treating them as point masses, assuming that there's symmetry and uniform density so that these things are right in the geometric center. So I'll measure their R1 and R2, and when I take them off, I'll also be measuring M1 and M2 on the scale to plug into this equation. But then I'll go ahead and do a run. So once these are fixed, I've measured their values, I'll let the hanging mass drop with Pasco running, and I'll get a graph of omega versus time, and from there I'll be able to get alpha. Right, so I'm going to call this alpha sub 1 because this is the first time I've run it. I'll get this value of alpha, and then I can plug it into this equation. I would have measured R2, wound and unwound, averaged it out. I can take the hanging mass off, put it on the scale and measure it, and then it would just be a matter of plugging it in. And then what I get is the moment of inertia of the apparatus plus all of the stuff. So if this is the apparatus, the stuff here is the rod plus the point masses. I just want the point masses. So what I'm going to do is to take one more run. So alpha 1, again, is associated with the stuff being the rod and the point masses. So right now, this is I of rod plus I of point masses. And this is the one associated with alpha sub 1. So I'll mark that here. The next thing I'm going to do is then to take off the point masses. So I have left just the rod. And I'll do another run. And I'll get another omega versus time, where the slope of the line is just going to be alpha sub 2. And then my I net with alpha sub 2 will still be I of the apparatus plus whatever other stuff is on it, but the only stuff that's on it is now the rod. So if I subtract, I plug in values into here, my new alpha 2, assuming I use the same hanging mass, which if you can use the same hanging mass, it's better. You might have to alter it at some point though, because the less stuff you have on here, the faster it goes and the harder it is to get good data. But if you still can use the same hanging mass and that same radius, then the only thing changing is alpha from one run to the second run, and that you've taken the point masses off. So all you have to do is subtract these two, and that will give you the moment of inertia of the point masses. And that's it. You'll compare that to m1 r1 squared plus m2 r2 squared. And those steps are outlined for you in the lab, which I've put on campus. You'll use the same method to measure the moment of inertia of a solid disk and a ring. So for part 2 of the lab, what you're going to do is you're going to put the disk, you're going to mount a disk on here. There's a hole through its center and you just kind of bolt it on. And then you put the thick ring. That's the one with the inner radius and the outer radius. That's substantial. So here's my thick ring. This mounts right onto the solid disk because the disk has like 2 little holes in it, and the ring has like 2 little feet that fit right into it, and they lock in place. And just make sure that they're rotating together. You'll see that there's the 2 little feet fit right into there, and you should be able to rotate them together. So this is all one rotating object. So now, if I take a run, right, I'm getting I net, which is I apparatus plus I of the stuff. So I take a run, let's call this I3, or alpha 3, excuse me, is the slope of the line now. Alpha 3, if I run it, is I of the apparatus plus I of the disk plus I of the ring, the thick ring. That's my I stuff this time. So I want to find just I of the ring and compare it to 1/2 mr squared, and 1/2 m r1 squared plus 1/2 m r2 squared, the other theoretical value that I have. So what I'm going to do is I'm going to remove the ring and do another run. I'll get alpha sub 4, and I net with alpha sub 4 now will be I of the apparatus plus just I of the disk, because that's all that I have left. But I also want to find, so, okay, hold on, excuse me. So the difference between these two, after I plug in my alphas, will just be I of the ring. I want to find I of the disk, so what I do next is I also remove the disk and I do another run. I get a 5th alpha, and my I net for alpha 5 is now just I of the apparatus. When I plug that into here, I take the subtraction, I get back I of the disk. One tricky point on this is that your hanging mass is probably going to have to change from here to here. So you probably have a new hanging mass that you have to insert in here, because this is so light that if you use the 50 gram plus mass hanger that's out there, this thing is going to accelerate really, really quickly. And this may not be able to get any data. You might be able to get like 2 data points, and it's not going to look like a line. You want to make sure that your data is looking linear. And if it's not, that means you have to adjust the hanging mass by adding more or taking away some. In this case, when it's just the apparatus alone, you're probably going to have to maybe just use that mass hanger or a very light weight itself, in which case this will be changing. And you'll have to account for that. You'll see that there are tables in the lab where it asks you what is the hanging mass for each run. So if you adjust it, you're going to record it. You can also adjust the radius, because you actually have 3 choices, 1, 2, or 3. But I recommend highly using the center one. This one is just too big for the actual apparatus. It doesn't work. And this one, there's too much error, because when it's wound and unwound, it's so small that it actually makes a significant difference. Anyhow, so you'll probably just want to change the hanging mass. So this is the data that you're taking, and you're really just subtracting these values from one another to find moments of inertia for the disk, ring, and point masses, and comparing them to the theory part A that you've already determined. So this is the bulk of it, except for at the end there is a propagation of error. So it asks you to propagate the error for the ring. So let me just erase this. If you remember, the ring is just the difference between these two. So what that would look like is inet alpha 3 minus inet alpha 4. So that would be MHGR2 alpha 3 minus MHR2 squared minus the one for alpha 4. If you use the same hanging mass, these terms will just subtract, but it may not be, you might have had to change it. So if you don't change it, this would be like hanging mass 3, hanging mass 4 over here. So they might be different. To propagate the error in this difference, well, you'll have a minimum of 4 terms in the propagation of error. So this is I of the ring. Alpha sub 3, it has its own uncertainty. You actually get it when you graph omega versus time and you get the slope of this line. Because you'll get alpha sub 3 plus or minus the uncertainty in alpha sub 3. You'll be picking that right off of the graph. Same with alpha sub 4. So alpha sub 4 will also have its own uncertainty. The hanging mass, if you only use 1, then you'll have 1. If you use 2 from one to the other, then you'll have 2 values of the hanging mass, and then uncertainty will just be from the single measurement, which is the precision of the instrument. And R sub 2, it has the uncertainty that you determined from measuring it wound and unwound, averaging it, and calculating the standard deviation. So you have a minimum of 4 terms. If you change the hanging mass, then you'd have 5. If for some reason you change the radius, you'd have 6. And that's in the propagation of error. So if you look at part 3, it asks you to propagate the error in this moment of inertia, and then it also asks you to go back to the regular equation for the ring. You would have measured the mass of the ring and measured the mass of the radius of that thing independently. These are your comparative values. So you will also propagate the error in just these 2 terms, where you've only measured them once, so the precision is the uncertainty. So, because I forgot, same with the eye of the disk. You'll also be measuring the mass of the disk and its inner and outer radius as a comparative value. I feel like that's everything. I can't really show you the apparatus, but Tyler said there was one set up when I left on Thursday, and there should be 2 set up hopefully by the next time we all come in. So if you have any questions about the apparatus, please ask Tyler or me. Otherwise, I hope this has been helpful. Best we can do. All right, I'll see you guys as soon as the smoke is better. Bye.